Hello and welcome to Alpha Omega training videos. In this video, we are going to delve into the simulation of the wind flow over a villa building, and after that, we will do the post-processing and extract the graphical results of different parameters available and defined in the simulation. Stay with us. At first, I open my Ansys Workbench software, and this is my solved project. Here you can see the geometry, which is around in the design modeler software, and after that, the design geometry is imported into the Ansys Meshing in order to generate elements. The mesh file then is imported into the Ansys Fluent software, and the solution is solved successfully. Okay, let's take a look at the geometry and the elements of the solution in the Ansys Meshing software. Alright, this is the geometry. I can hide some of the faces, and this is the building. You can see the building, and these are the boundary conditions defined. Here is the inlet boundary condition. The wind flow enters the domain from this boundary condition. By clicking on the mesh, you can see the elements of the project. We can also define a section by going to the home section plane, and here I define this line at about the center of the geometry, and this is my section plane. I select it, and here I select the show whole elements, and this will show you the 3D types of the mesh file, and you can check the elements. Okay, that's it, and let's get back into the Ansys Workbench software. In order to enter the Ansys Fluent software, here I right click on the setup and edit. Okay, here in the Fluent Launcher window, first you can see the dimension options, which is selected as 3D by default. Under the solver options, you can see the double precision. This option in Ansys Fluent software is a computational setting that allows for more accurate numerical calculations. This option uses 64 bits to represent numbers compared to the 32 bits used in the single precision. The double precision effectively doubles the number of significant figures in the calculations, leading to more accurate results. So here I enable the double precision. And here under the parallel, you can see the option solver processes. This option is a feature that allows you to control the number of processes used for the soft solver. I change it from 4 to 12, and after hitting start, the Ansys Fluent software will be loaded after a few moments. Alright, the mesh file is imported successfully, and here you can see the geometry of the solution. To take a look into the inside of the domain, you can select the display mesh option, and here I disable the surfaces of inlet, outlet, and symmetry. Alright, this is the geometry of the villa building. You can also see the elements, surface elements, by enabling the edge option. After that, you can check your mesh file by clicking on the check option, and here, after seeing the work done in the console, and also make sure that the minimum volume value is not a negative value. After that, by clicking on the report quality, we can check the elements quality using two different parameters, which the first one is minimum orthogonal quality, and the second one is maximum aspect ratio. In Ansys Fluent, the aspect ratio refers to the ratio of the longest edge to the shortest edge in a cell. It's an important metric for mesh quality. Fluent can't handle high aspect ratio cells, but for better accuracy it's recommended to keep it below 100. However, in boundary layers it can be several thousands. In case of orthogonal quality, it is a measure of the cell's deviation from a perfect shape. The range is 0 to 1, where 1 represents a perfect cell. Lower values indicate poor quality, potentially leading to inaccurate results. It's crucial to maintain high orthogonal quality, preferably above 0.1, to ensure accurate and reliable simulations. Okay, after checking the quality of elements, here under the mesh we have the solver type, which is selected as pressure based by default. The pressure based solver is primarily used for incompressible and mildly compressible flows. This solver uses a pressure correction method to solve the Navier-Stokes equations. The step involved include guessing the pressure field, solving the momentum equations to obtain a velocity field, and then correcting the pressure field based on the divergence of the velocity field. The process is then iterated until a converged solution is found. This solver is efficient and suitable for a wide variety of flow problems. The velocity formulation is absolute, and in case of time, the solution is steady state. Also, the effects of gravity are neglected. For the general section, we have the models. Let's dive into the fascinating world of Ansys Fluent models. Ansys Fluent is a powerhouse of computational fluid dynamics models. It includes turbulence models to simulate the chaotic motion of fluids and multiphase models for scenarios where different phases of matter interact. But that's not all. Fluent also offers heat transfer models for thermal analysis and reaction models for chemical reactions. Need to simulate combustion? No problem. Fluent's combustion models have got you covered. And if you're dealing with species transport, Fluent's species transport models are at your service. All these models are designed to help you simulate the most complex fluid dynamics with ease and accuracy. So get ready to unlock new levels of understanding with Ansys Fluent. In this project, the only model that we are going to use is the viscose model. Here you can see a variety of options for different turbulence models and also different near-wall treatment models. The standard K epsilon model in Ansys Fluent is a popular turbulence model used for a wide range of computational fluid dynamics applications. It's a two equation, as you can see here, that provides a general description for turbulence by means of two transport equations: the turbulent kinetic energy, K, and its dissipation rate, epsilon. This model is renowned for its robustness and economy regarding computational resources, making it suitable for a variety of industrial applications. After models, we have the material sections. The material section in Ansys Fluent is like a wizard spellbook, brimming with potential. It's a treasure trove where you can define and manage the physical and chemical properties of materials in your simulation. With it, you can create, modify, and delete materials, and also define the properties of fluids, solids, and mixtures. Think of it as your personal library where you can experiment and push the boundaries of material science. Whether you're working on heat transfer, fluid dynamics, or chemical reactions, the material section gives you the power to simulate real world conditions accurately. Here for the project, the air is defined. You can double click on it and see the properties of air using two parameters, which the first one is density and the second one is viscosity. You can also have access to Fluent database by going to this section. After that, the Sazun condition. This section is like the conductor of an orchestra harmonizing the symphony of your simulation. It's a powerful tool that allows you to specify the physical models, materials, and boundary conditions for each cell zone in your domain. Imagine being able to control the very fabric of your simulation universe. You can define fluid, solid, porous, or moving deforming zones, each with its unique properties and behaviors. Moreover, you can also specify source terms, adding an extra level of customization to your simulation. In our project, we just have one cell zone, and there's no motion, there's no porous zone or fan, or there's no laminar zone, and also source terms. At the next step, we have the boundary conditions. By double clicking on it, you can see the different boundary conditions defined in geometry or mesh generating software. I want to classify them by their type by hitting the zone type. The first boundary condition is inlet. Its type is velocity inlet. By double clicking on it, you can open the velocity inlet window. Okay, As you can see, the initial gauge pressure is set to 0. The coordinate system of velocity is set to Cartesian, and the x velocity, y velocity, and z velocity are defined. The turbulence options are leave as default. The next boundary is interior, which shows the uh, interior domain of the solution, and there is no option for it. The next one is outlet. In the outlet boundary condition, just make sure that the gauge pressure on the outlet boundary conditions is set to 0. And also leave the turbulence options by default. The upper boundary condition is assumed to be symmetry. This is the symmetry boundary condition. And we have two wall boundary conditions. The wall is the ground, and the wall part 1 is the walls of villa building. The options for both of them are the same. By double clicking on them, you can see that the wall motion is defined as a stationary. There's no motion, and also the no slip condition is set for shear condition. Alright, that's it for the setup section. Here I close the setup, and next we are going to check the solution options. In the solution section, the first option is methods. By double clicking on methods, you can see the different pressure velocity coupling schemes, the flux type, and special discretization methods in this window. As you can see, the simple scheme or the semi-implicit method for pressure linked equation scheme is selected for pressure velocity coupling. This scheme is a numerical procedure used for solving the Navier-Stokes equations, which describe the motion of fluid. The scheme is iterative and relies on guessing and sequentially correcting the pressure and velocity fields to achieve a converged solution. It's widely used due to its simplicity and efficiency, especially for incompressible and steady-state flows. The flux type is set to Raycho and momentum based. The Raycho momentum based and distance based, which is here, are used for pressure velocity coupling in simulations. The Raycho momentum based flux type is the original method which is used to avoid the checkerboard pressure pattern by introducing a momentum interpolation term in the pressure equation. It works well for structured grids. Okay, under the special discretizations, we have the gradient option. For the gradient, the least square cell based is selected. The least square cell based gradient method for special discretization is an approach used to calculate gradient vectors to scalar quantities in the flow field. The method works by minimizing the sum of the squared differences between the values of the scalar quantity at the cell centers and the values predicted by the linear approximation of the scalar quantity over the entire cell. This method offers a higher level of accuracy compared to other methods like the Green-Gauss cell-based method, specifically for unstructured and non-orthogonal meshes. However, it may require more computational resources due to its complexity. Okay, after that, our parameters such as pressure, momentum, turbulent kinetic energy, dissipation rate, and the second order upwind is chosen for them. Okay, here I want to show you the different options, which is second order, standard pressure, linear, body force for pressure, and for momentum it's first, second order, quick, third order, and the options for the turbulent kinetic and dissipation rate are same as momentum. The first order upwind method is the simplest and most robust discretization scheme, but it has a high numerical diffusion which can lead to lead to inaccurate results. The second order upwind method improves upon the first order by using information from two grid points, reducing numerical diffusion and improving accuracy. Quick or quadratic upstream interpolation for convective kinematics is a third order discretization scheme that uses a weighted combination of second order upwind and central difference schemes, providing even better accuracy. Finally, the third order upwind method is more accurate than the second order, but it requires more computational effort. The primary difference among these methods is the trade off between accuracy and computational effort, with higher order methods providing increased accuracy at the cost of increased computational effort. Okay, for our project, we have select second order for all of our parameters. After that, we have the controls section. And here you can see the under relaxation factors. URFs uh, are a numerical technique used to control the convergence of the solution in iterative methods. It's a factor by which the computed change of a variable is scaled down to avoid potential divergence or oscillations in the solution process. The range of under relaxation factor in Ansys Fluent generally varies between 0 and 1. A value close to 0 means that the solution will converge slowly, very slowly, while a value close to 1 means that the solution will converge faster, but it may lead to instability if the value is too high. Next, we have the report definitions. Users can create various types of reports such as surface reports or volume reports. Here, if you right click and go to the new section, you can see the options. Surface reports, volume reports, and also flux or force reports. Now, these reports can contain information about the flow field like pressure, velocity, temperature, and more on your desired boundary conditions. In the monitors, if you open it, the first option is residuals. In Ansys Fluent, residuals represent the imbalance in the solved equations and are used to assess the convergence of the solution. When the solution is perfectly converged, residuals would theoretically be zero. However, in practice, due to numerical errors and approximations, residuals tend to reach a small value and then level off. Here you can see the absolute criteria of the residual for each of the equations in the section. Here are the equations, and also make sure that the parent console and plot options are enabled. After that, we have the initialization section. Initialization in Ansys Fluent defines initial conditions for the computational domain, setting the starting point for the calculation. Standard initialization sets uniform conditions, while hybrid initialization uses potential flow solutions to initialize the flow field, useful when the initial state is not well known. In our project, we have set the standard initialization and the compute from is set as inlet boundary condition. So the software will assume that at the initial state, the uh, flow all over the domain is like the inlet boundary condition, and this is the value of wind in all of the cells. After hitting the initialize, the solution will be initialized. And finally, we have the run calculation section. Here we have to enter the number of iterations. The iterative mode of calculation is a critical process that is used to solve complex problems in a step-by-step manner. The software divides the problem into smaller, manageable parts and solves them iteratively until it reaches the final solution. This method is particularly useful when dealing with nonlinear problems, where the solution is not directly proportional to the input. The software continuously refines the solution in each iteration, providing a more accurate and precise result. The iterative method also allows for better control and monitoring of the solution process, enabling users to make necessary adjustments to achieve optimal results. Okay, if I hit the calculate, the solution will start to get solved. In the next section, we will take a look at the results and extract the graphical views from different parameters of the project. Okay, finally, after about 450 iterations, here, as you can see, the equations are converged and the solution is ready to extract some results. Okay, to do that, here under the results, I open the graphics, and at first I can take a look at contours. This is the contour of static pressure on the wall and ground and wall of the building below. Also, I can see the velocity magnitude over the building. Here you can see the vortex generated. Okay, we can also uh, see the contour and the geometry at the same time by going to the scene. Here I double click on the scene. This is the contour 2, and I defined a mesh, which is the geometry, and save display. Alright, this is the contour beside the geometry. You can also save the picture from graphical view by clicking on the save picture option. Here you can set the format of your figure, color and type, and also the resolution. Alright, the next option is vectors. You can see the vectors of airflow. Here you can zoom in and check it accurately how it behaves over the building. Let's go to the scene and select vector and mesh, and that's it. Also, we have the streamlines or path lines here. These are the streamlines realized from inlet boundary condition and colored by static pressure. We can change it to, for example, velocity magnitude. That's it. In the scene, I enable the path line and mesh. We can also enable the contour at the same time. This is a very good view. Okay, that's it. The simulation and post-processing of this project is successfully completed, and I hope that you have enjoyed this solution.